Hey, hi everyone. Thanks for coming this is the first of our Earth Sciences Research Group seminar series at Liverpool. And for the first week, we have a talk from Anthony Lamur, a postdoc here at Liverpool. So we thought we'd celebrate the first one by doing a hybrid, in-person and virtual seminar. So yeah, I hope you can hear okay virtually. We've not done this before, so hopefully it will all go okay. Anthony's going to give his talk now, and then at the end there'll be time for questions. And if you're watching on Zoom or YouTube, please just put your questions in the chat or ask them at the end, and we'll ask them to Anthony on your behalf. So Anthony did his PhD at Clermont, in Blaise Pascal University at Clermont-Ferrand. He then did the first year of his master's at Michigan Tech before coming back to finish it at Clermont, and he did his master's in volcanology. So he then had a gap year whilst trying to find a PhD and ended up coming to Liverpool to do his PhD with Jan Leverley on the mechanics of fracturing and healing in magmas. He then did a short postdoc with Jan before completing a 2-year university teaching position in geophysics. And he's now working as a postdoc with Jan again on the permeability and compressibility of magmas. So thanks again for coming, and I'll now hand over to Anthony.
Thanks, Caitlin. So I'll start sharing.
In magmas. He then did a short postdoc with Jan before completing a 2-year university teaching position in geophysics. And he's now working as a postdoc with Jan again on the permeability and compressibility.
Okay. No, that's fine. I've paused. Hang on, I've paused it. Does it work? Does it work on YouTube? Yeah. Okay, so it's just paused on mine. Then it's fine. It's not. Sorry, this one. Okay. Right, so can we hear me everywhere? So, well, here is fine, but on Zoom and YouTube. Yeah. Okay, so hi everyone. Today I'm going to talk about transients in volcanic materials. So basically what happens when you look at volcanic materials at different time scales, but also spatial scales. This is basically work that I did partly on my PhD and also partly in a small research contract I had at the end of 2021. So volcanoes and volcanic environments in general are quite heterogeneous environments. So you'll have the edifice itself that is basically made up of different layers. Eruptions is basically setting them on top of one another. These layers will have different mechanical properties, but also different reaction to flow properties. Beneath the edifice, you will have magma intrusions, either dikes or sills, combination of both, laccolith, and all of these features that will affect the surrounding. And the surrounding is basically made up of either other igneous rocks or sedimentary rocks. Often also associated to volcanic edifices, you'll have some sort of tectonic settings, so a fault of some sort, a thrust or a normal fault. And this fault will also have a damage zone that is going to be associated to it that will also change the fluid flow properties around the edifice in the hydrothermal system, and may also affect the stability of the volcano itself. So these volcanic environments are just extremely heterogeneous, and as I said, they just build up over time, and they result from the interactions of different types of stresses. So mechanical through compaction or tectonic stresses, or the circulation of fluids, and thermal due to the movement of hot magma, and then the cooling of this magma will also change the stresses around the volcano. So what that means is that the fluid circulation around this volcano is going to be extremely complex and will affect all types of stresses inside the volcano. They will change rapidly on short time scales, but also, as I've shown you in the small schematic before, can be at extremely small scale, but also at extremely large scale. So therefore, understanding how these fluids move is extremely important to understanding multiple hazards of volcanoes. So today what I'll do is basically focus on the interplay of the evolution and development of damage, or basically feature that can allow for a more efficient, allow or disallow more efficient fluid circulation. So basically I'm going to look at this interplay between those two. Just as a quick context, if we look at the damage in rocks and magmas in general, that green line here is basically what is referred to as a brittle ductile transition. So on the left side of that green line, you have brittle deformation. On the right side of that green line, you have ductile deformation. In terms of characteristic, really simply, brittle deformation is going to be normally more localized and will lead to dilation in the rocks and will generally sustain little strain to rupture. On the other hand, ductile deformation is going to be distributed throughout the body of rock or magma and will lead to compactions, therefore closing of pore space. And that mode of deformation is usually going to be able to sustain a lot more strain. So now if we take, just say, one example of a volcanic rock, that's that blue line. If you increase the effective stress, so basically if you increase the principal stress on that rock, it may cross that green line and go from a brittle to a ductile type of deformation. But then if you because you go to ductile deformation, you close the porosity, you close the pore space, and you might be able to come back to a brittle deformation. So already here you can see that in the time scale is really important. Just for one example, we can see that we can cross that brittle ductile deformation twice. So what can affect that brittle ductile deformation? So that's been published by one of our previous PhD student. Obviously the porous network or the porosity, so how much pore space is there. These sharp drops here are characteristic of brittle deformation. Whereas like these more curved lines here are more characteristic of a brittle deformation. So these will be less porous rocks and these would be more porous rocks. There's also going to be the strain rate. So these rocks are basically the same as these ones, but they've been deformed, all of them 10 times slower. And what we can see is the disappearance of the brittle deformation regime. And all the rocks deform ductilely. And of course, for magmas, temperature. So the blue line here, it's again the same rocks than these ones. And the blue lines will be the brittle deformation and the red ones would be high temperature ductile deformation. So we have all of these parameters that can change the brittle ductile deformation. And in magmas and rocks in volcanoes, all of them are going to be present. So we have to understand pretty much a lot of variables to be able to tackle the mechanics of volcanoes. So then, as I said, there's going to be the spatial and the timescale the timescale I've already talked about, but also the spatial scale will also affect the brittle ductile deformation. If we go at really small scale, and that would be, for instance, a pore, you apply a stress around that pore, and that pore will generate a crack due to a stress difference, due to its shape and the stress differences around the pore. So you have, at small scale, brittle deformation. But if we go to a larger scale and look at all the pores and minerals inside the rock mass, these deformation is distributed throughout the whole body of a material. And larger scale here, we have a ductile deformation for the same applied stress. And then if we continue again to apply that same stress, these micro cracks might percolate together and generate a larger crack. So again, that time scale of is really important in the brittle ductile deformation transition. So one natural example from that is a paper from a PhD is columnar joints. Columnar joints were formed by volumetric contraction of the magma while it cools. And that volumetric contraction generates a random network of microcracks that are pervasively distributed throughout the magmatic body. So while these microfractures develop, we have a ductile deformation that happens. But then as the cooling progresses, these cracks again will coalesce and generate hexagonal sets of cracks that will form the columnar joints. And that's then the brittle deformation. So as I said, I was going to talk about the interaction between damage and fluid flow in volcanoes and stresses. So really schematically, all of them basically affect one another. So if you increase damage due to an increase in stress, you're going to change that stress field. And that stress field might change the fluid flow, but that fluid flow change might also change the damage. So therefore, we have that continuous loop that's changing. And therefore, it's important to understand for volcanic hazards. So understanding the scale and extent of this deformation mean that the geophysical signals that we monitor at volcanoes can be really ambiguous to understand. And especially in a time frame that is variables for risk reduction. And basically what we need to do is to do small scale experiments, whether we're doing it on rocks or whether we do analog experiments, we do smaller scale experiments to try and tackle fundamental processes that help us understand better these geophysical signals in nature. So now I'm going to go into the first result part, and I'm going to focus on a rather large scale. So the interaction between tectonic faults and volcanic environments. And the research question I had here was, can the repetition of elastic stresses generated by either the fault itself or by magma migration, can these elastic stresses create damage in volcanic materials? So sampling wise, we took a rock that is highly repeatable, basically in terms of uniaxial compression strength and permeability. We also wanted to be able to sustain quite a prolonged period of creep deformation to survive the experiment. And then we did measurements of permeability, porosity, and solid density, as well as VP before the experiment. During the experiments, we measured acoustic emissions at quite a wide scale. And then we measured, of course, actual stress and strain, and as well as radial strain. And after the experiment, for all the samples, we measured permeability, porosity, and VP again, just to see if there was any changes induced by the experiment. So today I'm going to basically talk mostly about the permeability and VP and axial stress strain curves. The samples are 30 andesitic samples from Colima volcano in Mexico. We can see that from the permeability measurements that they are all really close to one another. They're well within one order of magnitude in permeability, so they're really repeatable. They all have similar porosity between 10.7 and 13.2, so that was quite nice range. And they all have, importantly, they all have the similar permeability reduction with pressure. So what that means is that in terms of mechanical response to increase in pressure, they are all pretty much doing the same thing, which is what we wanted. So the experiment, we did the first type of test is a normal UCS test where we want to induce a brittle deformation. So we deformed at 10 to the minus 5 strain rate, so and then up to failure to measure the peak stress. That was about 70 megapascal for all the 3 samples tested. Then we did a creep experiment where we basically loaded at the same speed, then let the sample at that stress condition for 6 hours, and then unloaded that sample at the same speed. We did the creep conditions at 3 different percentage of the peak stress, so 60, 65, and 70%. And then the third type of test we did was inducing mechanical oscillations during the creep phase. There were 15 oscillations spaced by 26 minutes between each of them. And these oscillations, we also varied the amplitude of the oscillation of 2.5, 5, and 7.5% of the load hold position. So that's done for all creep tests, all creep conditions, and all amplitudes. In the next few slides, the blue is going to be showing you the different shades of blue is going to be showing the creep condition. So light blue is going to be the lower creep condition, and dark blue is going to be the higher creep condition. And then the stars are going the size of the stars are going to show you the size of the amplitude of the elastic waves. In terms of acoustic emissions, the normal UCS tests were quite typical. So where you have first quite a bit of AEs generated during the compaction phase of the test. Then during the elastic phase of the test, we have little to no AEs generated because no damage should be accumulating as much. And towards failure, we see an acceleration in AE showing that micro cracking that is ductile, but then coalesces into a big fracture at the end when the fracture happens. During the creep conditions, what we see, well, pretty much not much. All of the AEs are generated during the loading phase, which is pretty much corresponding to that to this increase here. And then for oscillation tests, the same thing happens. So we see most of the AEs are generated during the loading phase. But what we can see as we start increasing the amplitude, and that might be a bit small for this, but the next one is quite striking, is that you see as these oscillations are being generated, we see a small burst in acoustic emission. That's a lot more striking for the large amplitudes. So you can see that these dashed lines are each of the oscillations. And then every time we do have one of these oscillation events, we have a burst of AE generated with it. So that suggests that there is micro cracking that is associated with these oscillations. So then mechanical results, what I was interested is to look at how much how much deformation was happening during the creep condition, during the creep phase. So that is going to be termed epsilon C for the next few slides. What we see from these results, when I compiled all of these epsilon C, what we see is that the higher the creep condition, so the darker the blue on this graph, the more strain at creep we attain, which is quite nice because that's what you should have. If you're closer to the failure point of the rock and you leave it for the same time, you should have a bit more strain. Then when we have the oscillation, what's striking is that we have a lot more, at least twice as much, or 2 to 3 times as much strain at creep than during the creep test. There does not seem to be a clear correlation with the size of the oscillating event, or the creep dependence here doesn't seem to appear either. So basically no color or no size arrangement in here. The only thing that's striking is that it's a lot bigger strain at creep during these oscillation tests. So in the next slide, next few slides, sorry, I'm going to use these. So I'll ask you to remember those. So epsilon C is going to be the strain at creep during the creep tests. Epsilon CO is going to be strain at creep during the oscillation test. Okay. Then when I looked at the individual strain events, what we see is that the dark, the black one is the first oscillation event that I introduced, and the light blue is the last oscillation event in one test. I've done the comparison for all of the tests, and for all of the tests, what we see is that the strain response through the test, as the test progresses, is actually being reduced compared to the first event. Okay, so the more event you have during those tests, the more the strain response decreases. So then we use this called dynamic time warping to stretch each of those. This is quite a cool technique, and it's used on everyone's phone today. It's basically a spatial recognition, vocal recognition software use that technique. And what it allows is to calculate the distance between two straining points. Two straining curves. The sum of all this, of all events together, what I can get is the accumulated strain throughout the test, and therefore compare how much strain were accumulated in different oscillation type. Okay, so like here is the small amplitude oscillation test for all the samples, and then the large amplitude the large amplitudes for all the tests. So what we see is that there is a general trend that larger amplitude or larger oscillation are introduced will accumulate more strain. What's quite interesting is that during one of my tests, one of the samples failed, mechanically failed. And that was the only one sample that also accumulated more strain than the average strain at failure during the UCS test. So that's a good, that graph shows that basically this might work in terms of I accumulate more strain, and therefore I will be fracturing the sample as the others have failed. Okay, this one I'm going to call it epsilon A, so accumulated strain. Now, if I assume that the strain accumulated during the oscillation events is a combination of the strain that is accumulated during the creep phase, but also the strain that is accumulated by the individual oscillations. What we can find is the fraction of this accumulated strain that is transferred from elastic to inelastic. And again, what we'll see is that larger strain or larger oscillations will transfer more strain to the sample, or will basically create more inelastic deformation in the samples. Okay, bigger oscillation, more strain is being transferred to the sample. Again, this group condition here doesn't seem to really influence how much the strain is transferred to the sample, just the oscillation. It might be a bit confusing for now, but like it does all make sense when you bring everything together. So when I looked at the Young's modulus, so the initial is from the loading phase, and for these, it's during the unloading phase. What's quite weird is that if I introduce damage in a rock, the Young's modulus should be going down. That's pretty much what we see in every literature. Here, it goes up. So am I actually doing any damage to these rocks? Also, there doesn't seem to be a clear correlation between either creep or oscillation. It just increases during the unloading phases. This change is bigger during the oscillation test. So if there is damage that is being created, this would create more damage than this. in terms of VP, we have a similar thing that happens. Basically, that's before the experiments and again after the experiments. There's no clear correlation with creep oscillation, only that oscillation tests will result in a bigger change in VP after the experiment. So I've interpreted this as being basically a form pore-emanated cracks during these oscillation tests. Well, all the creep, but I form more of pore-emanated cracks during the oscillation test. And the result for the Young's modulus is counterintuitive, because what I think happens is that these pore-emanated cracks will have some frictional resistance during unloading, and therefore give an apparent stiffening of the rock. And that goes opposite of what people have shown in the literature. And also that these pore-emanated crack might be able to, depending on their size, might be able to either act as a waveguide for my P waves or as reflectors, and therefore give me an apparent change in velocity that is either increased or either decreased, depending on their size, their orientation, and everything. So what that means altogether is that the bigger changes in both of these variables tells me that there is more damage created during the oscillation test than during the creep test. And if you're not convinced yet, then the permeability is basically the final nail in the coffin here. In our rig, the confinement is applied perpendicular to those cracks I should have formed. So therefore, the more I put them, the more pressure I put around them, the more crack closure I should have. So therefore, the bigger permeability reduction I should have. Okay, so that's what it should see. So like the more damage, the more the permeability should change, the faster the permeability should change with increasing pressure. So what I did is, as I said, measured the permeability before and permeability after. So, and then take the slope of these changes. I've normalized to the low confinement pressure just to get rid of the effect of, well, the sample variability pretty much. But that's always normalized to the sample's low confinement counterpart. So when we look at this, what we see is that the permeability loss rate or the permeability change rate is actually becoming more negative, or that's a negative slope. So like the bigger that value is negative, the more the rapidly changes. And again, that permeability plot shows me that oscillation test will produce more damage than during the creep test. So therefore, some of this elastic energy here in the oscillation test is actually transferred into the sample and create inelastic damage. So elastic wave create inelastic deformation. Yeah, just said that. So I'll summarize pretty much all of this is that during my tests, these sigma 1 applied will generate these pore-emanated crack. These will, as you put the oscillation, you'll create more of these cracks and then generate burst in AE, or the cracks will be larger. The damage that is accumulated during the strain, the strain that is taken by pretty much forming these cracks will, at the next oscillation event, give an apparent reduction in straining. The larger, and what I've shown in the last few slides is that the larger oscillations convert more inelastic strain into the samples. These results in changes in mechanical properties. So we have Young's modulus that is increasing due to these cracks having frictional resistance during the unloading, but also depending on the size and the orientation of these cracks will have a more drastic change in VP with more damage. And if we compress, well, if we apply confinement perpendicular to these cracks will form more if you have more, and therefore you have a larger permeability decrease. with confinement. What's important though is that here what I show is the damage or the inelastic strain is being created by the repetition of these elastic stressing events. And what's important is that because those elastic oscillations elastic deformation should always come back to, if you remove that elastic strain, it should come back to its original position. Here, what it shows is that if you repeat low amplitude elastic oscillations, you will end up generating inelastic damage, so not recoverable strain into materials, and therefore you're going to fatigue this material over time. Some implications for this is that I found that that paper online is a dike event or magma migration event under Paricutin volcano in Mexico. And these are the moment tensors inversion during before a tectonic earthquake. What we see is that the dilation events are mostly in a northeast southwest trend, and the compression events are perpendicular to these. After that, there is a tectonic earthquake between on June the 7th, and after that, basically the moment tensor inversion just goes into any direction. So what that suggests for me is that this earthquake event has created damage underneath the volcano, and this damage has now changed for time being. I don't know if they've redone that study now, but for at least for that study, they show that there is quite a change into the moment tensor inversion. So therefore, a lot of damage has been created. And these basically why I think this type of event is important is that if you have a large amplitude elastic wave that generated during an earthquake, close to the epicenter, you'll have damage that's going to be created due to the shear amplitude of the oscillations. But if you go further away, these waves will attenuate, and at some point you'll be well within the elastic response of the materials, and you should not therefore create damage far away from the epicenter. But now take a repetition of earthquake, like far enough of a fault, and you might actually generate damage into buildings or damage into slopes, like mining slopes or anything like this. So therefore, it's quite important to know that. On volcanoes, what's really important is that during magma migration, you have the generation of thousands of low amplitude earthquake swarms prior to the eruption. And these, even if they don't physically break the rock, will weaken the rock, and that might affect the stresses underneath the volcano and change the hydrothermal system and destabilize it and end up in, like, for instance, a phreatic event, or it can change the slope stability and start triggering flank collapse, and therefore like the other suite of hazards associated to them. Okay, so that's for the damage accumulation. Now I'll move on to a lot smaller area, and it's basically the top few hundred meters of the conduit. I don't know, it's really hard to tell how much, but for those of you in Liverpool, you might have seen the next few slides. The research questions for this is, can we quantify the timescales for fractures to disappear in magmatic conduit? So again, like you have a damage, you have a large damage, like can we make it disappear after time? And then what are the physical processes driving fracture healing in silicate melts? So a quick explanation of like how silicate melts mechanics work is silicate melts are really good at forming glass. And glass is important for volcanoes because depending on how fast you deform the magma, you can fracture it by going too fast. You can cross the glass transition, or you can, if you change the temperature, if you go from hot to cold, you can fracture it as well. Same as what we've seen for the columnar joints. So what we interested in here is going to be these ones here. So we're going to stay at the same temperature, but I'm going to change the time scale of my experiment. So I'm going to go fast. I'm going to break the rock. I'm going to break the glass. I'm going to go slow. I'm going to heal the rock. So I'm going to go from an elastic to a viscous liquid response. A good example of the glass transition is in churches. The really old glass windows will be thicker at the bottom and thinner at the top. If you throw a rock at one of those, well, probably don't do it on the church, but if you throw a rock at one of those, you're going to break the glass, so fast strain rate. But over a long time scale, that glass, even if it appears solid to us, over a longer time scale, it still behaved as a liquid. Okay, that's an example of that. What that means for volcanoes is that the melt being able to fracture is a good way to release a rapid stressing event, but also healing means that you can then therefore recover coherence into the material if you leave it for long enough. That's just a small video of glass. It doesn't want to play, I guess. Nah. So the experiment setup is that I have glass rods that are put into a furnace and heat up above the glass transition temperature. So I'm going to be in that red regime here. And then I'm going to pull apart I'm going to apply a constant stress for a long time. And then I'm going to pull apart to fracture the glass. So to cross a glass transition, I'm basically going to be going through that cycle over and over again. During this, I'm going to look at the peak stress that's being generated by the contact. And I've done that on 2 different glasses, and they are standard glasses so that we have well-constrained chemistries. And then I've tested one of the glass at 3 different viscosities, so 3 different temperatures. What we see is that the strength recovered by the contact is increasing as we increase the time of contact, as you would expect. So more time, you'd have more healing. So here 1 would be fully recovered, and well, 0 is it's on logarithmic scale, but like this would be like basically not recovered and then recover that 1. We see that healing is slower at higher viscosity. So higher viscosity is lower temperature. So that's also quite intuitive. If you have a more viscous glass, it's going to take it longer for it to recover strength. It is chemistry independent. So triangle are one type of glass, and then the red dots are the same condition for the other glass. So same viscosity, but for the other glass. And what we see is that they recover strength at the same rate. So it might mean that at least for these 2 standard glasses, healing is chemistry independent. And importantly is that we see that the healing will start after a characteristic onset time. So for the triangle, it's about 15 seconds, 30 seconds. And like for the orange, the characteristic time scale is going to be about here. Okay, so I've calculated those later. This characteristic time is proportional to the viscosity of the melt. And that's important because then we can get rid, knowing this relationship with the relaxation time scale of the melt, or like how fast you're going to cross how fast you need to cross the glass transition. This allows us to get rid of the viscosity effect and go look into the kinetics of healing itself. And when we do this, so when we basically normalize the time of contact by this onset time, we find that healing has two different regimes. We have a first linear regression here. There's a slope of 3/2. And that's characteristic of a wetting. Okay? And wetting is where atoms are going to be diffusing parallel to the fracture plane. And that's going to be distributed along the fracture plane. But it's basically not crossing the fracture plane yet. And at some 50 times the onset, well, at normalized time of about 50, we see a change in regime that goes with a slope of 1/2. And that 1/2 is characteristic of a diffusive regime where we now exchange material across the fracture plane. Okay, and that's going to be mostly what the healing is going to be made of, but it always starts with a wetting dominated regime. So we can see that in our experimental product. So this is a natural obsidian where we see that there was a fracture, and then you can see that this fracture starts disappearing at places. And this is one of our experimental glass rod, where you see like these trails of pores that are being trapped in between solid glasses. And that's the remnant of the healed fracture plane. And that leaves basically a trail of isolated pores. What it's important for is that, for instance, for volcanoes like Santiaguito, we see that the eruptions are generated along fractures, and that these fractures, and at Santiaguito, these eruptions happen at a time frame of about every half hour in general. So what we suggest happen here is that basically, rather than having magma that's coming up to the surface every 30 minutes, what you end up having is a magma that is bubbly underneath like a hot cap, and that hot cap is actually able to generate fractures, allow these gases to escape when the stresses have built up too much. But then once the stresses have been relaxed, these fractures, well, the dome collapsed, the dome falls down a bit, and these fractures are being pushed into contact together again for a period of time. And then therefore they're going to start healing and then regain coherence. So here we don't need to have magma coming up to the surface. What we just have to have is actually these fractures developing and healing inside the dome itself. So if we, that's just sort of like thing I've played with in the last few years, is if I now, what we could do with this is take one of these healing curves and then generate pressurization rate, or model different pressurization rates, and see when this the fracture curve is being crossed by these curves, and where it crosses gives you the time between eruption. But I mean, that's just basically playing. That's something we could go forward with. Another implication for fracture healing, and it's not my work, it's from Jackie Kendrick, would be to look at seismic drum beats underneath volcanoes, where Jackie suggested that as you during a friction experiment, what she sees is that there is a regain in coherence of the material every time the samples are being put into contact, or every time the sample are being shortened. And both of that for different chemistries. So what that could mean is that basically that viscous break is as the shear fractures are being generating friction will generate heat, and heat will basically cross the glass transition on the horizontal scale, heating that viscous break by basically lowering the viscosity and hastening the healing process. And that's only one part of like the friction thing. And that's, again, also just speculative here. It's just an implication like this. So just to basically, then now what I'm going to be doing is that we've seen that this damage is transient, right? It can be created through the passage of elastic waves, but it can also be regained by healing in magmas. It can be regained, well, it can be destroyed by minerals healing in hydrothermal system. So like this damage is never going to be staying open and staying there for fluid circulation to be there. And the same happens inside magma. Like these, if we look inside an actual thin section of the magma, there's a lot of things that happens in that image. Is that there is a fracture plane that goes from about here, goes down and then goes up again around there. Then you have a really more like tiny pores here and then massive pores on the side. But here the pores are connected, so they're going to be able to carry the flow quite easily. On that side, the pores are isolated, so the flow is not going to go. At the same time, you have a fracture that can heal and so on. So like inside a volcanic conduit, you have all of these processes that happen at once. So we have to characterize and understand these permeability measurement, or how the gas escape the systems. We have to start looking at more dynamic measurements and not static as what we do normally in the lab. And as they are always changing, that's a lot more complicated. And it's basically what I'm going to be doing in the next few years. Is we're going to use a specially designed triaxial press to do in situ measurements of magma deformation and permeability measurement at the same time. And we'll be able to do that in different stress fields. And we're going to combine that with micromechanical models as well, to try and basically tackle this problem of dynamic permeability inside rapidly changing material. Okay, so hopefully we'll try and get a better understanding of this gas accumulation and release at volcanoes, and what it does to the apparent compressibility of the magma. And that's important for the geophysical signal at the top of the volcano. So quick take-home points. I am not sure I'm doing on time, but basically what I wanted to say, well, what I wanted to show is that damage is never going to be static. It will change due to changes in stresses, changes in fluid circulation. But then all of these are interplaying with one another, and therefore we have to understand all of them working with one another to understand hazards. And then the two main results that I wanted to remind you is that repetitive elastic oscillation can induce pervasive damage, inelastic damage in the material. And also when it comes to considering volcanic eruptions, understanding all of the processes and the timescales at which they are happening is important to understanding the geophysical signals we see. And that's it. Do we have questions? It's quite weird to be clapped at the end. Do we have any questions? Yes, Jenny?
I have a question. So, really interesting talk, thanks, Anthony, and thanks for being our first person to try the hybrid version. So you talked in your section about damage accumulation. You were talking about like getting more damage in material and things like that. And I wondered like about your starting materials, like you showed they're behaving quite similarly, and so it's kind of representative, but then in the end is the damage homogeneously distributed? You sort of showed in the schematics kind of focused to maybe at bubbles and crystals and things like that. But does the damage, is it sort of homogeneous or is it more localized?
Well, the bad thing is we, because of the Young's modulus test, we did a UCS test on all of our samples. We broke them. So we can't really do a thin section of a full sample. I can redo one of these experiments at the higher amplitude and look at the damage. So short answer is I do not know because I've not looked into it. But I would assume that actually, yes, it will be generated. But when we see the UCS test, normally they will be generated along a plane that's kind of, well, the macro fractures will normally be about 45-degree angle to sigma 1 into these samples. So there might be a more like distributed along this, but I would still assume that actually there will be also fractures, the microcracks are generated off that fracture plane. But I'd have to do another experiment and actually do a thin section at the end of it to just see. Yeah. Another question? Yeah, Dan.
So, yes, I think well, just a quick comment on this question. The microstructures are really interesting because you have that schematic diagram showing the cracks emanating what cause inclusions and things in the sample. It would be really nice to see whether that's actually what the real sample is. So yeah, just with the cyclic stuff, it's really interesting that these things seem to stiffen up when you put these oscillations in as well, because you get these acoustic emission bursts, so you are creating new crack damage potentially. You get this some kind of a signal there which suggests that. Yet the samples are getting stiffer, and that's shown by that pressure sensitivity factor, and that the permeability doesn't decrease quite as much over the pressure range as it did to start with too. So, any thoughts about what's responsible for that? Because in pretty much every study I've seen, I guess up to now, putting new cracks in always makes rocks more compliant. So yeah. So it's pretty effective.
Well, the thing is normally, well, for the studies I've read about this, actually, it's like they would normally do one experiment, measure the Young's modulus, unload, and then reload it, and then see whether like the Young's modulus changed. Here, I measured the Young's modulus during the loading phase and then during the unloading phase. So, and my interpretation of the stiffening is because literally those cracks that are parallel to sigma 1, when you start unloading them, we'll have like small frictional resistance that will give apparent stiffening to the rock that is actually just due to the geometry of the experiment.
So you are measuring the elasticity on the unloading
part? Yeah.
Okay. So there's a paper by Clinton and Walsh, I think, in 1962, where they talk about backsliding on cracks as well. So that's how they explain that hysteresis that you get from loading to unloading, the difference between the loading and the unloading path. Obviously, you get different gradients there as well. Yeah. So, I can put that page to you.
Yes, please. Yeah. No, I've not. Might have read it, but I'm not sure I've read it actually. So yeah, that'd be great. Yeah. Another one? Yeah.
The fracture healing that you spoke of, do the same physical processes apply to some larger scale fractures, like when dikes close up? Is that the same thing happening?
You have to cross that glass transition, right? Okay, so like if it's after a dike has like inflated and deflated, if it's like the host rock that comes back, unless you are able to melt that rock and then just basically become to like having viscous processes across the fracture plane, if you are able to have that maybe you'll be able to close the crack. But normally what I would assume is after the dike has passed, if it ever kind of like shuts down properly, that you might not have melted or like it quenches as soon as the melt has passed. I don't know for dikes. You just need to have the viscous processes across the along and across the fracture plane to be able to start healing. But that'd be interesting to see if we can see that in the field, maybe. Yeah, Josh.
How representative are your amplitudes for, say, like magma flow and like the drop beat size?
I have not done scaling things. Well, just I've not done scaling of the amplitudes to natural material. All I wanted is stay in the elastic regime, so where I should not be able. Well, whenever the oscillation is finished, I should be coming back to the original strain. So I've not done scaling properly. I don't know how. I don't know how it relates, really. We could do like a paper on this. Could do like just calculate how big and where from an epicenter, whatever could be. Yeah, another question. Do we have questions online? No. No. Okay. Is there any? Is there two things in the chat here?
That's just from.
Okay. Fair. Should I stop sharing then? And yeah, cool. Cool. Yeah, thanks. And then should we just end the session?